Welcome to our YouTube channel. This is lecture 2 of organic chemistry where we studied a reagent in our last class, that is N-bromosuccinamide. So similarly we are going to study another reagent which is very helpful in our organic chemistry, that is LDA, which is abbreviated as lithium diisopropylamide. So before going to its properties, functions, applications and etc., let us study its structure. You can see here it contains two propyl groups attached to the same nitrogen atom, which is containing a negative charge, and here you can also see the lithium ion carrying positive charge. There's no bond formation between them, but they are electrostatically attracted towards each other since they have opposite charges. So when you, if you write it in a bond line structure, the structure looks like this. So next, let us see the preparation of LDA, that is lithium diisopropylamide. It is prepared by using diisopropylamine and butyl lithium, which is a very strong base under temperature below room temperature, that is at 0 degree Celsius, using a solvent called THF, which is also abbreviated as tetrahydrofuran. So by using these reagents under this condition, we'll get diisopropylamide. That is, we have two propyl groups attached to the same nitrogen atom, and our nitrogen atom is having a negative charge, and Li plus from this butyl lithium will be attached or attracted electrostatically towards this negative charge, and will get butyl hydride as a byproduct. So this is all about the preparation of LDA. You can see the mechanism here, that is the butyl lithium abstracts hydrogen from here, and it is removed as H plus, and this bond is shifted and on this nitrogen atom containing two propyl groups. Hence, it contains a negative charge. So next, the properties of lithium diisopropylamide. So LDA is a very strong base, but it is not a good nucleophile. So since it is a very strong base, it can abstract hydrogen, but it does not act as a very good nucleophile. That is, it cannot be used for addition of nucleophiles or in any nucleophilic reactions. And the second point is the structure of LDA is very large. That is, it contains two propyl groups, and the structure is somewhat large, and it acts as a hindered base. That is, in a molecule, if there's a presence of a large atoms or a large sites, it acts. There's a steric hindrance between the molecule and this lithium diisopropylamide. And the next point is it abstracts acidic hydrogen from less hindered site or from an active carbon. That means, since we know that it is a strong base, strong bases abstracts hydrogen which are acidic, but this LDA abstracts with less acidic protons, acidic proton from less hindered site or from an active carbon center. And the next point is, next properties of LDA is it is used to create a carbanion or enolate anion from carbonyl group containing compounds. So using LDA we can create intermediates like carbanion, or we can also create an enolate anion from the compounds which have having carbonyl group. So now let's look up to the application part. There are so many applications of LDA in organic chemistry, but the two important applications of this reagent is, one is alkylation, that is nothing but addition of alkyl group to our given reagent, and second one is alpha salination or just salination, which is nothing but addition of saline group or side group to the given compound. So this is all about the application part, and now let's look into some of the examples. First, let's see how LDA is used in alkylation. So you can see here I have taken a compound where we have an electron withdrawing group, that is COH. It is a electron withdrawing group. So the adjacent carbon are containing hydrogen hydrogen are acidic. So we know, as I said, as we study in the properties, the LDA abstracts the hydrogen which are less acidic. So since we have electron withdrawing group here, this carbon adjacent to it will be having a acidic hydrogen. So LDA abstracts hydrogen from this CH3, hence since it is less acidic compared to the hydrogen at this position, which is more acidic, because here CH3 is an electron donating group, so it will be less, the hydrogens present in this CH3 will be less acidic. So the LDA abstracts these hydrogens and creates an anion here. So next, as we studied, we have create LDA is used to create a carbon ion. So we have now here created a carbon ion. So from this, now next we are going to alkylate this with by reacting this with the alkyl halides. So now we have negative charge in on the CH2 carbon, and you can see since this X denotes a halogen, it will be electronegative and it carries partially negative charge, and this alkyl group acts as an electrophilic center. Now this nucleophile center attacks the electrophile center, and this halogen will be removed, and finally we'll get this product where we have alkylated this carbon. So now let's see another example. Here in the second example, you can see that it's a carbonyl compound. So in the properties, we have studied that the compounds which are having carbonyl groups, when reacted with the LDA, they form an enolate ion. In the enolate ion, here you can see that there are acidic protons in these two positions, at this CH2 and this CH3. But as we have studied in the last lecture while studying about N-bromosuccinamide, I have explained the reactivity order that methylene is more reactive than this methyl, since it has the lone pair, and which is highly unstable and very highly reactive. So our LDA abstracts the proton from this CH2, and it forms an negative carbon ion here, and this negative charge can resonate, and this double bond is shifted on the oxygen. So now our oxygen atom carries negative charge, and when it is subjected to alkylation using the alkyl halide, this our alkyl center is also, this R acts as an electrophilic center, and the nucleophilic part attacks this electrophilic part, and the halide ion is removed. That is how the alkylation process takes place, and we'll obtain this compound, alkylated carbonyl compound. So next, let's see another example. Before going to this, let's see this example where see here you are having a carbonyl compound. Here you have two sites where you can find acidic protons or acidic hydrogens, one at this carbon and another at this carbon. Since our LDA is the properties of LDA is, while studying the properties of LDA, we have studied that LDA is a very large base, so it attacks the left indirect side. So now it prefers to abstract proton from this side, since it is less inert than to abstract the proton from this carbon. So by abstracting proton from this position or from this carbon, it creates a carbon ion here. It creates a carbon ion at this position, and next our intermediate is subjected to alkylation by adding with an alkyl halide. So now this carbanion center attacks this electrophilic pH and that is phenyl group. Since our phenyl act as an electrophilic center due to the presence of a high electronegative group that is bromine here, will obtain our product that is this position or position